5.1 is probability distributions, and you've got a lot of vocab here. All right, so let's take a second. A random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome for a procedure. All right, this is specifically what we are looking for. It's going to be a numerical value, so it's going to be a number. We want to talk about the number of whatever's happening. And there could be 0 or 1 or 2 black markers or whatever the situation is. A probability distribution is some kind of description of all of those probabilities. A lot of the times it's a table. We'll have a table showing all of the probabilities for everything that could happen. Discrete random variable. Discrete means the same thing as finite, and it means something that's countable, something that's possible to count, whereas continuous means the opposite of finite, so it's infinite and impossible to count. All right, so we've got those kind of definitions, but I think random variable is the most important one. Random variable is literally what you're talking about in the problem, and you're going to need to find a number for how many of each of the different values that it could take. Probability distribution requirements. Every probability distribution must satisfy these 3 requirements. There is a numerical value, not categorical. It's not categorical. It's a number, not a word. You should recall what sigma means. Sigma, this Greek letter means we're going to sum them up. It's talking about a sum. It's talking about adding them all up. And so we're going to add up all of those probabilities, and all of those probabilities add up to 1. This thing says that those probabilities are all in between 0 and 1. So you've seen this before. Talking about probabilities, so of course they have to be between 0 and 1. Example 1, coin toss. Complete the probability distribution for random variable x where the number of heads when 2 coins are tossed. So x equals the number of heads. That's really important. This is our random variable. So x can take on several different values. X is going to be a number because we want the number of heads. So we're flipping 2 coins. A lot of the times it's a good idea to look at the sample space. Sample space is what could possibly happen. Well, we could flip 2 coins and get heads and heads, heads and tails, tails and heads, or tails and tails. This problem is simple enough that we can look at the sample space. So if you think about the probability distribution, we're talking about how many heads could appear. And so if you notice, there are 0 heads here, there are 2 heads here, and each of these has 1 head showing. So the values for x could be 0, 1, and 2. That's the number of heads showing up in this problem. 2 coins flipped. Then we've got to look at our probabilities. Px is just talking about the probability. So the probability of 0 heads showing up is just this one thing out of the 4 possible outcomes. It's 1/4, or 0.25 if you'd rather. 1 head showing up, well, there are 2 different ways of doing that. And so it's going to be 2/4. 2/4 reduces to 1/2. And then lastly, 2 heads showing up has a 1/4 probability. Now, a couple of things you should notice that each of those probability numbers are between 0 and 1, and those 3 probability numbers add up to 1. All right, so we still are talking about a probability distribution here. Probability histogram is the exact same thing. It's just a picture instead of a table. So we're looking at like a bar graph kind of deal. We've got 0, 1, and 2, and we've got the same probabilities, 0.25 and 0.5. I think this formula is insanely difficult to understand, but this formula is a formula for calculating those same numbers that were in the table. I think it's way, way easier to do what we did and look at the sample space. But if x is 0, we're finding the probability of 0, which we already know from the table above is 1/4. But how this formula works is, let's let x equal 0. The formula says 1/2 times 2 minus x is 0 factorial, and then x is 0 factorial. Now it's important to know that 0 factorial is just defined as 1. 0 factorial is 1. Otherwise, we're just going to calculate this. There's 1 on the top, and then we've got this 2, which is just 2, and then inside parentheses, 2 minus 0 is 2. So this would be 2 factorial. 2 factorial is 2 times 1. So 2 times 1, that's going to be 2. And 0 factorial is 1. We're looking at 1/4. So it calculates the exact same thing as what we found above. It's that 0.25. It's 1/4. We could do the same thing for x equals 1 and x equals 2. I just don't know that it's worth our time. But that's a probability formula for this situation. Example 2, hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution? Yes or no? Couple of problems. And you'd have to go back to those 3 criteria shown above. Remember how the values of the random variable were supposed to be numbers? These are not numbers, so that's a problem. Okay, that means this can't be a probability distribution. Those things are supposed to be numbers. X equals 0, 1, and 2, or something like that. It's like how many heads showed up, or how many black markers. So that's no good. And then 2, you had to have the sum of the probabilities was equal to 1. So is that true? If we add up all these probabilities, are we going to get 1? I don't think that's going to work either. And you can add them up, add those 4 values, and I can't remember what you're going to get. 1.57 maybe? Yeah. They add up to 1.57. That's supposed to equal 1. It does not. Third criterion says all of the probabilities have to be between 0 and 1. And that seems to work. That's the only one that seems to work. But you can't whiff on those 2. All 3 of those things have to be present. So no, this is not a probability distribution. Parameters of a probability distribution. Remember that with a probability distribution, we have a description of a population instead of a sample. So the values of the mean, standard deviation, and variance are parameters, not statistics. In an earlier chapter, we had a mnemonic device that said population, parameter, sample, statistic. I like how they kind of bring you back to some of the definitions from earlier, but we're talking about parameters. Mean, and then they give you this symbol, mu, is given by the sum of x times px. You take each of the values of the random variable times its corresponding probability. You add those together. Variance is sigma squared, and that's a lot harder to calculate. There's 2 different ways of doing it. They're telling us one way, it's easier to understand. Another way is easier for calculations, but those are variance. And then lastly, we have standard deviation. That's just sigma. So we've got sigma squared, we've got mu, we've got a couple of different Greek letters. And I think an easier way of finding standard deviation is just if you understand that standard deviation is the square root of the variance. I think that's a lot easier if we do it that way. Standard deviation is the square root of the variance. And keep in mind, we talked about standard deviation a little bit last week. When we talk about standard deviation, we're talking about how far apart those numbers are. Okay, are all of the numbers the same? Like we talked about with the Yahtzee. When all 5 numbers were the same, the standard deviation was 0 because they didn't vary. But if the numbers are much different, standard deviation will be much higher. The expected value of a discrete random variable x is denoted by E. And E is just the same thing as mu. It's the mean value of the outcomes. And so it would make sense that we have the same exact formula for E as for mu. Number 3, this table describes the probability distribution for a number of heads when 2 coins are tossed. Find the mean, variance, and standard deviation for this probability distribution. So they're giving us the same probability distribution that we came up with earlier, but we need to find mean, variance, and standard deviation. So what we have to do is, for the mean, we're going to take the sigma, or the sum, of each of the x times px values. So in this case, for 0 heads showing up, we're going to have 0 times 0.25, which equals 0. And we're going to have 1 times 0.5, which equals 0.5. And we're going to have 2 times 0.25, which is 0.5. What we want to do for the mean is we want to add those things up. Well, you add those things up and you're going to get 1, right? 1.0. So there's your mean, your mu. Mu equals 1.0. That's the mean. For the variance, that one's a little bit harder. We want x minus mu squared times px. Px is just probability. Remember, x is the number 0, 1, or 2, and mu is that mean that we just found. So we're going to find each of those, and we're going to sum them up. In the first case, the first x is 0, minus our mu value of 1, squared times the probability value was 0.25. 0 minus 1, that's negative 1. Squared is 1 times 0.25 is 0.25. Feel free to use a calculator if you'd like. 0.25. The next one, the x value was 1. The mu value was 1. Squared times the probability of this one was 0.5. We've got 1 minus 1 is 0. Square root of 0 times 0.5 is still 0. Lastly, x is 2, mu is 1, squared times the probability value was 0.25. That's going to be 1 squared is 1 times 0.25 is 0.25. So again, what we want to do is sum those up. 0.25 plus 0 plus 0.25 is 0.5. That is your variance, your sigma squared. Sigma squared is 0.5. That's variance. Standard deviation is actually the easiest one to find because all you have to do is remember standard deviation is square root of the variance. Square root of the variance. So standard deviation is square root of the variance. So square root of 0.5. It's about 0.707. So now we have the mean, the variation, and the standard deviation. Range rule of thumb we've seen before. It's talking about significantly high and low numbers. I think it helps that you might be more comfortable with these symbols. Remember, mu is mean, and sigma is standard deviation. So what this says is mean minus 2 standard deviations, or mean plus 2 standard deviations. Those are talking about significantly high and significantly low. So when I look at this problem, number 4, we found that when tossing 2 coins, the mean number of heads is 1.0, and the standard deviation is 0.7. Notice they rounded off. Use those results and the range rule of thumb to determine whether 2 heads is a significantly high number of heads. So they want significantly high, so we're looking at this value. Mu plus 2 sigma. Well, mu was 1.0, and we're going to multiply that times 2 times 0.7. We're going to have 1 plus 1.4 is 2.4. How we read this is any number 2.4 or higher would count as significantly high. But we're looking at the number 2. We're looking at 2 heads. That's our question. Is 2 heads significantly high? These numbers tell us that it's not. 2 heads is not significantly high. So then they kind of give us a different way of identifying significantly high and significantly low. It says X successes is significantly high if the probability of that number or more is less than or equal 0.5, and we are significantly low if the probability of that or fewer is less than or equal 0.05. So we don't really have an example of that. We'll probably come back and hit that again later. If, under a given assumption, the probability of a particular outcome is very small, and the outcome occurs significantly less than or significantly greater than what we expect with that assumption, we conclude that the assumption is probably not correct. You gotta think about if your assumption is way, way off, you can assume your assumption's not very good. Whoops. Example 5, be a better bettor. You have $5 to place on a bet in the Golden Nugget Casino in Las Vegas. You're considering one of 2 bets. Part A says bet $5 on the number 7 in roulette. Remember roulette, you've got a big wheel, you've got black and red numbers, but 2 of them are green. It says the probability of losing $5, that's your whole bet, is 37 over 38, and the probability of making a net gain of 175 is 1 out of 38. In parentheses, it says the prize is 180 minus your wager. So keep in mind, you've got to pay to play. So you go up and you pay the guy $5, and you're going to win 180, but that's not your gain. Okay, if you win 180, your gain, your net gain is actually plus 175, right? Because you already gave him $5, right? If you win a raffle and you win $1,000 in that raffle, you're not up 1,000. You're up 1,000 minus whatever a ticket cost. So maybe $2. So you're up $9.98. All right. Here's what we want to do. We want to make a probability distribution here. And so when we look at this, you might say, well, what's possible in this situation is either losing or winning. We can either lose this game or we can win this game. But the problem is that's not good for my probability distribution. I need a number. We need to put a number on losing and put another number on winning. Okay? So our random variable x is basically, your change, your change in money. And so you can either lose $5 or you can gain $175. So we want to look at the probabilities of those 2 things happening. Well, we don't have to compute that because they just gave it to me. The probability of losing $5 is 37 out of 38, and the probability of gaining 175 is 1 out of 38. We see those probabilities add up to 1, so that's good, right? What we want to do is find the expected value. So the expected value is the same thing as the mean. It's sigma xpx. We're just going to find this, -5 times 37 over 38. And 175 times 1 over 38. We're going to find the sigma, find the sum. So we can say negative 4.868, negative 4.868. And positive 4.6, what was it? 05. I'm going to add those things up. We're talking about money here. So when you add that up, that's like going to be a change of like minus 27 cents or so. So, or 26 cents, I guess. That's your expected value if you play roulette. And what that means is that's kind of like the average. All right. You play that game, you're never going to lose 26 cents. But if you play that game a million times, your average would be you're losing 26 cents per play. Every time you play, on average, you'd lose 26 cents. You'll never really lose 26 cents. It's just your average. Okay. So that's not great. We would expect to lose that game. Let's look at craps. Craps, we want to do the same thing. So let's look at what could possibly happen. You could lose $5 or you could gain $5. The probabilities of each of those things, probability of losing $5 is 251 over 495, and the probability of gaining 5 is 244 over 495. So we want to do the same thing. We want to find the sigma of the x times px's. That's going to give you your expected value. So we've got about negative 253 and positive 246. Once you sum that up, you're losing 7 cents. Okay, now again, you're not really losing 7 cents when you play this game. You're losing 7 cents on average over the course of a lot of games. You play this game a long time. That's what you would expect, an average loss of 7 cents. So remember the question, which of the bets, or which bet is better in the sense of producing a higher expected value? Well, I'd rather lose 7 cents than lose 26 cents. So I would say craps is the better bet.